it'll go on my YouTube channel for now. Then I can later download it.
All right, sounds good. Okay, I think we can get started.
Sure. So today in this presentation, I'm hoping to discuss about a paper which introduced the method SHAP, which is a popular interpretability method. So I guess now this paper has around like 10,000 citations. So it was published in 2017 in New Lips. So yeah, so this is a paper by a group in University of Washington, and they want to sort of. So by the time in 2017, there have a lot of interpretability methods which tackle different sort of avenues. So this paper provides a unified theory about it, um, so that it will be more concrete to use in the literature. So in essence, this paper presents a method called Shapley additive explanations. So they, like for shortened form, they just call it SHAP. So this Shapley values is a thing which is used in game theory. So it's like a very old concept, but this is the paper which like brings that concept to interpretability and provides it in a unified theoretical manner. So they mentioned that by this new formation of theory, we can explain we can explain 6 of the previous methods in the literature. Then they provide different estimation methods for SHAP. We'll talk about this in a bit. So, so before going on, let's briefly talk about why we need interpretability and what is meant by interpretability. So, so in the sense, why interpretability? I think it's since we are all working in machine learning, it's a bit clear to us. So, we want so the thing is, in different domains of applications, there is a requirement for domain experts to understand what's going on this model or black box model. So model interpretability is very important for the trust that we need to build in the system. So because of this, so currently, uh, so most of the time, even though sometimes we develop deep methods, the practitioners or doctors or that community sometimes prefer simple models because the simple models, it's easy to um, interpret, even though the bit of maybe some accuracy degradement. So so practitioners sometimes prefer to simple ML models with that sacrifice on accuracy. So the goal of this paper is to focus on developing a method which can keep this accuracy while um, trying to interpret it. So that's the overall goal of interpretability or explainability in machine learning. So if we talk about what is interpretability is we need to explain uh, what the model does in understandable terms to a human. So, so there are like 2 things that we need to satisfy. One thing is this explanation should be faithful. So, so if we, so it must be accurate. So that's what we mean by point 1. And the other thing is we need to, so this actually depends on the context. So when we mention that something is understandable to, it depends on whether that person is a domain expert or um, so on. So maybe for a layman user, they might need more uh, details about that explanation. So when we talk about explanations, there are a few aspects we can talk about. So one thing is, if it's like a small linear model, we can just give them the parameters. So based on these parameters, we can simply explain what each feature contributes to the overall prediction. And so these are several types of ways in which we can convey the interpretability of a model. So another way is that we can give some example inputs and mention this is how the model performs. Or we can summarize the whole model with a tree or rule-based program. Um, then the other thing is, so this paper actually tackles this part where they want to uh, interpret what features are the most important. And also, this is also another way where they can, if we flip a particular feature, what happens? So uh, these are like several few directions. All has the overall goal of interpreting what happens. So, so as we talked about earlier, linear models, if we know these weights, we know what each feature contributes to the overall prediction. How in the complex models, we don't know. So the goal is that we need to derive some sort of values for each feature so that we can interpret how important that feature is. So I hope that sort of overall introduction is sort of clear. So in the
So, so
yes,
Ramit,
please.
here, what do you exactly mean by a feature in general?
Yes. So for tabular data, it would be like a maybe yeah. If we take a patient data, it could be whether a person has this trait or not. That sort of thing can be a feature. However, when it comes to images, it is mostly maybe uh, not to the pixel level, but some patch level that sort of can be contributed as a feature actually.
Okay.
All right. So in this literature, there are like two avenues of research where people try to build inherently interpretable models. So without any additional tools, they want to interpret the models or post-hoc explanation models. So the black box model we already have, we use some kind of tool to explain it later. So these are Lime and Shep. Those are uh, for examples for that method. So, all right. So now there's another terminology that we call local explanation. So local explanation means rather than describing the whole mapping, um, we try to explain one individual data point. So we try to explain the model's prediction with respect to particular data points. That's local explanation. And a global explanation is, as you could interpret, we are sort of looking at the overall integrating over the data mentioned and trying to derive a global explanation. So, so these are like a couple of methods that they use salience maps, prototypes, how close a feature is to the prototype, those sort of methods. So we focus on feature importance in this presentation. So before going on to the exact contributions of this paper, there's one thing that we need to clarify in our minds, which is called the Shapley values. So this is named after a mathematician called Clyde Shapley, so who received the Nobel Prize for game theory. So the problem is in a cooperative game, we ask the question, how much payoff do we need to give to each individual person? So that's the problem uh, that this scientist has addressed in game theory. So he has proposed the Shapley value as a possible answer to this question. So if we like interpret again, like let's say people are collaborating towards a business venture or something, and each person contributes in some way, and we need to at the end of the day we need to determine how much of payment should give each person based on their contributions. In other words, we are trying to uh, find the marginal contribution of each person. So I think this was introduced in 1985, I guess. So this was a well-known theory in game theory. So this paper actually unifies this theory to model interpretability. All right. So So we talked about Shapley value. Without going to machine learning, let's first look at how we can compute the Shapley value. It's actually somewhat simple. So the marginal contribution of a person is the reward with that person minus the reward without that person. So it's very intuitive. We need to, if we have a group of people, if that person is not there, how much is the reward that they get? And if that person is there, how much value could they earn? So this is that difference. However, the thing is, there are like a lot of permutations that we can think of when talking about this collective. So one thing is, let's say,
Wait, can you go
this
back?
person is
Can you go
sure,
back
sure,
the slide to the definition?
sure.
No, the equation you had, is it resource or is it reward?
Um, yeah, I think it should be reward. I actually meant like the overall output, that sort of meaning.
Okay.
Yeah. So when we try to calculate this, as we talked about, like the issue is this I person can step in at different times. So let's say this person is not there, but all these one, two, three, all these people are there. So when we talk about the marginal contribution of that person, it could be the scenario that at the beginning, all these other people were not there, and only this person was there, and then I person stepped in. So that's one instance of calculating this person's contribution. That means just one person was there, and I person stepped in. So it could be that these two doesn't like to work with each other. So as we can expect, there are a lot of permutations that we can think of when we talk about marginal contribution. So let's say this person a scenario where there are only two people, so x1 and x2, and it's just denote by this circle, which is like a function. So when x1 is passed to this function, we get a particular reward, and when x2 is passed to this, we get a particular reward, and these are like the inputs. So when we try to compute the marginal contribution of x1, we need to take the scenario where there were no people and x1 stepped in, and there was only one person and x1 stepped in. So those two are the only possible ways we can think of how x1 may have contributed. So actually, so then it's actually so if we take it by numerical terms, let's say because x1 stepped in, the business venture got $50,000 and x2 stepped in this much. And uh, let's say these values were already given. So if that was the case, we can simply calculate the marginal contribution like this equation. X1 stepped in, there was no reward, x1, x2. So this is fairly simple. So it could be the scenario where the people can like work in synergy. So because of uh, because of the expertise, maybe one person is good at something and another person is good at another thing. So because of that synergy, maybe when they get it, it could be a better value. So in that also we can simply calculate the marginal contribution um, considering those two scenarios. So the point I mentioned is that this can go down or go up based on that mutual dependence. So now, when it comes to like a higher order of people, like just to list these scenarios. So when we want to talk about three people, we need to look at a scenario where was two people and where there were one person and where there were no people. So these are like the scenarios before and after. So for all these values, all these instances, we need to have those values such that we can, so this is for n equals 4. So at the start, there are 3, 2, 1, and 0. So this is actually the number of subsets that exist. So the number of scenarios is like equal to 2 to the power n. Um, so, so in game theory, actually, we need to account for all these and weight these accordingly to get the actual marginal contribution. Um, all right. All right. So based on this formulation, Lloyd Shapley actually developed this like that notion of gain by adding a person, and uh, each of that reward is actually weighted by the number of possibilities out there and giving each weight, and we are summing over all the subsets where I is not present. So this is the reward we get with I present. This is without I, and this is all the subsets that could exist, like this one right here, these ones, and this one. So that this is what the Shapley value equation explains. Actually, this factor term doesn't we feel intuitive at first, but after rearranging, it's basically counting the number of possibilities at each of these uh, subset sizes. So that's what it means, giving equal weightage to all, like equal weightage to all of them. All right, so this is the Shapley value equation. Now, if we go back to machine learning, so by 2017, there have been numerous methods for interpretability. So some were about um, optimization-based techniques. These three were actually based on the Shapley concept, but they were not much efficient in computing. So this paper by Rupin Washington, they actually unified all these concepts, mentioning that all these individual methods are like a subset of this broad theory that they present. Um, so the theory in the sense like they define certain properties and mention that these individual methods fulfill some properties, um, and they actually uh, derive that they actually point out that the Shapley values are the things we need to compute. So, so now let's look at what they propose. So they talk about a method called additive feature attribution method. So, all right. So when we talked about the method SHAP, so SHAP is the method this paper introduces. So it, as the name suggests, it was Shapley additive explanations. So what we want to do is when we give a feature importance to one feature, these individual features should add up to uh, they should we should be able to concretely say that if this feature contributes by this amount of amount, it could be negative or positive. So they talk about a model to explain this concept. Uh, yeah. So this is just a diagram where we have model, and we get a prediction, and the explanation method also gives some value. All right. So, so they talk about uh, they mention that uh, the explanation that we talk about, this explanation method itself uh, can be thought as a model. So this model we denote by G. So we have that initial F model, and this method proposes to think about the explanation method as model itself. So they define this model in this equation. So this is actually pretty simple. So what this says is uh, this explanation model is a function of these binary variables. So these binary variables say that if a feature is present or not. So if there are m features, we have a binary vector, and each of those indexes say that um, whether that feature is present or not. So basically, this is like the uh, like if we like represent it as the individual uh, ith elements, we can uh, show it in this way. So basically, for each index, we are giving we are trying to compute the feature effect. So that's what we denote by this symbol. And if we forget about this entire summation, this is like the average, like DC shift sort of value if all the features are turned off in the sense. So this is the definition that they produce for like the method Shapley additive
So,
explanation.
Rabit, can
Yes,
you go back? Can you go back to that model diagram?
sure.
Uh,
This one.
yeah, this one. So GZ dash is actually the metric that is given by the model explanation method.
Yes. Um, yeah. So this is F, and this is actually data point, and this is G. So through some sampling technique, uh, we call it Z dash for a particular instance. So they try to so the thing is this X is like the normal data record. So this is called an interpretable vector in the sense as we talked about, it's a binary vector. So for a particular data point X, we can get a Z hat value, which represents it as a vector of zeros and ones. So those zeros and ones represent whether a feature is present or not. And for that feature presence vector, we compute a value.
Okay, so what you say is like, let's say you have M features. So now the dimensionality of C is M. It's a M
Yes.
dimensional vector and each entry is 0 or 1.
Yes.
So that's a combination of, in some sense, that's a combination of features, right? One combination of features.
Yeah. So there can be multiple instances where we can manipulate certain features to be turned off.
Okay. And can you go, that part is clear. Can you go to the next slide then?
Sure.
So here, okay, so this is like the functional form of GZ in some sense.
Yeah.
And so this pi 0 and pi I, they are like not defined at this point.
Yes, they are defined at this point. Yeah.
So they depend on the exact model. Like they do, are they functions of f with respect to the previous equation?
Yes, they are they depend on the black box model. Yeah.
Okay. And pi 0 is, what's the definition of pi 0?
Yes, we can think about it as the yeah. It's sort of an average prediction. So let's say in the model, if we set all the features to 0, what's the prediction? That's sort of so yeah, it's sort of a average value. If none of the features are present, it's sort of the average.
If none of the features are present, I think that then that would be a different thing. Like that would be a constant thing, right? And you will get
Yes,
some value.
yes, this is actually a constant.
Okay, yeah, that is a little bit unclear to me, but yeah.
Yeah. At some point they mentioned like if we give a, so in the picture we can think of it as giving all black pixels, something like that. But let me clarify
Okay,
further on.
I see.
I also uh,
I
don't have a
see.
good explanation. But
And for example, of pi I is based on the
you mean I? Sure.
I equals 1 to
Right.
m. Yeah.
Yeah. So for the ith feature, how much that feature is worth. So so when we are like, if we have a feature vector like this, and if this corresponds to the age, let's say this index corresponds to the feature age. So
Okay.
if we only have the age, what sort of feature effect is giving out from that I value is the uh, fee. So this is
Okay.
a binary variable. It actually means, let's say we have a tabular data set and we have features like age, previous medical admissions, those sort of columns. So each of those columns, so after we run Shapley, after we run Shap on a data set, what we want to get is individual phi values for each of the features.
Mhm. Okay, so that is, yeah, I think at this point, what I don't understand is how exactly that phi value is calculated in a sense. That's not the
Yeah.
output of f, right? Mm.
Um, this phi.
Yeah.
No, that's not the output of F. The paper, what they actually go on to say is that this is actually the Shapley values.
Okay, I see.
So that we talked earlier.
Okay.
Yeah. So based on this definition, they present some some constraints, some properties. They actually provide three properties. I actually have not listed in this presentation, but what the paper proves to say is that to satisfy these properties, these should be the Shapley values which was introduced in game theory, like how we compute each of these fees are through the Shapley value equation. That's what they prove.
Okay, yeah.
So now if we try to interpret these fees, so yeah, I haven't talked about the exact like proof and theorems they go through to say that. So basically, they came up with this additive feature attribution model, and they to in order to for this metric to be fair, they provide three properties, and they prove that these phi i's need to be the Shapley values in order to satisfy those properties. However, I have not included my presentation, but I'll talk about the talk from the point where these how Shapley values can be related to machine learning that we talked earlier. So in the Shapley that we equation we talked earlier, if I quickly go to that again. Yeah, so we had this equation where we consider all the possible subsets and give some weighting to it, and then we sum all this up. So this can be similarly extended to like a machine learning problem where these Shapley values depend on the black box model F and a particular data point. As we talked about earlier, we are only talk about a particular person at this point. So we need to compute this for a particular X value. Then this is, so let's say this is like the data record X where there are multiple features. So as we talked about earlier, like Z dash for mathematical um, definition, we talked about that this is like a 1-0 vector. So so this actually means so this is okay. So X, we have a lot of features. Let's say m number of features, and if we particularly sample one subset, so these gray ones are turned off. So we sample a subset uh, where age and body mass index is only present. So that's what this means here. Now we get rid of this ith feature that we are interested to calculate the Shapley value for. So then we get a so this is like that game theory example. If we think about this as two people, if what's the reward if there are two people, and what's the reward if um, the ith one is not there. So we are computing this for age. So because of that, we need to compute this value. Um, so we need to do this for all the subsets. So if there are m number of features, there's like 2 to the power m number of subsets that we can sample. So in order for that value to be accurate, what Shapley values introduced is that we need to compute it all over the subsets. And this is the weighting factor that we need to give for each of the example scenario. So this is very much similar to the that example we talked earlier. If I So basically this term means the gain by adding a particular feature. The thing is we need to do that for all the subsets. So this essentially means that we need to sample all the subsets and do this. So what this paper presents is that for this additive feature attribution method, it's actually Shapley values. But the problem is, as we discussed, there are a couple of problems. The one is, how can we compute this value? So our machine learning models are trained on a particular m number of features. So we cannot like simply train another model for only 2 features. It's not like feasible. The problem is, if we have m number of features, how can we like disable one feature and get that reward? So that's one problem. And the other one is, in machine learning, we deal with a lot of features. So how can we solve that? So if we want to turn off a particular, so if you want to sample a particular subset of features, but this paper goes on to says that they can like imputed random values to this features that we do not use. So that's one thing that they say. So basically, by randomness, we want to sample that feature out. So that's one approximation sort of thing that they do. And the other one is actually, since we have 2 to the power n subsets that we can sample from. So if we talk about 4 features, it's like 16 possible subsets. But in ML, we like work with a lot of features. So it's not feasible to calculate this for every like subset. That's the main issue. So even though the equation is like this, it's not straightforward to compute. So like with this unification of theory, such that this is actually something from game theory, they further like their main contribution is how to calculate this, and this constraints that they put to sample the particular features that we're interested in. So what they do is, since we have a lot of combinations of like since we have a lot of subsets that we can sample from, they actually sample only a feasible amount of those, and they actually train a linear regression to calculate that value. So they call this kernel SHAP. So basically, rather than computing all the possibilities, they actually run a linear regression to approximate those values. Unfortunately, I did not go to the exact details of it. But in essence, that's what they contribute there.
So
Yeah.
to see if I understood this right at a higher level. So the problem is like, so simple n here is the number of features. Is that right?
Sorry,
Or not?
sorry, I switched the slides. Is this
Okay.
capital M is
What
the number of features? Yeah.
features and the number of combinations? How do you get the combination?
It's actually the combinations are 2 to the power m. I have an n here, sorry.
Okay, so
2 to the
this
power
should be 2 to the power m.
Yes, that's the amount of combinations that we need to consider in order to evaluate the importance of one feature
Okay,
because of those permutations.
I see. So what they're saying is like actually like the contribution is getting this 2 to the power m number to some manageable 2 to the power some other number, which is more manageable
Yes,
to calculate. And what's the regression thing?
yes. So yeah, so rather than computing all those 2 to the power n combinations, the sample like they consider only I do not know the exact value what they sample, but when they sample, um, the thing is we have like these binary vectors like this where we sample from. So what they do is they fit a linear regression to this. Yeah, so yeah, the exact way of fitting I could not actually include in the presentation, and I didn't get familiar with it. Um, yeah, but the essence is like when we are calculating one feature's value, we can sort of through linear regression we sort of approximate, since we have some examples where that's turned on, like a lot of examples where it's on, we sort of approximate that importance rather than going over all the possible combinations.
So this is still like the one value 1 pi I.
Yeah, so this is
Okay,
one I, I, and
okay,
also it's only for a particular data point.
data point. Okay. So anyway, I can think about this as like they have some approximation to this right hand side with
Yes,
only smaller amount of terms.
yes, Tisha.
Okay.
That's the approximation. Yeah. So, uh, like, yeah. So with that approximation, like intuitively, what those Shapley values mean is that when we add a particular feature, how much of importance that it has. So uh, we only talked about for a particular data point as of now. Unfortunately, I could not get familiar with the exact details of like doing this to the whole data set. I suppose they get rid of the like data dimension by going over all the data points. That's what as an overview, I understood. Uh, so in that way, for the whole data set, we can compute these five values such that it does not depend on a particular individual data point. Yeah. So that's actually the sense of what I had prepared. Um, yeah. So like the this work is actually like used in a lot of applications and theoretical stuff as well, like with a lot of applications. But I think there's like other emerging methods which say the shortcomings of these methods. Um, yeah, so I'm not exactly familiar with that, but I think there are like number of ways to influence these Shapley values based on some adversarial techniques. So, yeah. So these are sort of the references I use for the presentation, but I'm happy to like discuss about any other.
It sounds good. One question is like, so this is 2017 paper, right?
Yeah,
Uh,
yes.
is this sort of like still kind of like the more go-to method to interpret things, or are there more novel work
Um,
that are more like accepted in a sense?
Yeah, I think this is like the most referred to model, most referred technique. Um, but the thing is, I have seen some methods which actually so so these methods give some value feature like value to each of the features. So now there are some techniques where uh, they train a like language model, post language model, which I like briefly seen. So they some people develop like an interface to the model where they can ask the model why they made this prediction. So I have seen that sort of direction, like a recent paper, but maybe it's not adapted well. I mean, as of now. So that sort of emerging, like innovative ideas are also there. Basically, we can reason with the model why they came to the conclusion
I
through
see.
natural language.
All right, sounds good. Any other questions?
So, Rahul, like I have a question, so can this method kind of like how can be used for like let's say for images or like something like time series data like compared to just tabular data, how it can be used,
Right, right, right.
and also
Yes.
like how would the complexity would be because so as you mentioned like
Right,
when they're
right.
running the kernel itself they have to go through all the data points and then they find the particular kernels particular combinations and then they use it. So how that can be useful for somewhat like let's say if the data is somewhat like a time series.
Right, right, right. Yes. So I'm not exactly familiar with the time series, but in the image situation, what they do is they like mask out pixels on like super pixel level. Um, yeah, time series. I'm not actually familiar how this is used. So as you mentioned, this kernel is very important such that we don't exhaust ourselves with respect to the data points that they have. So so there's like follow up couple of papers where they define these kernels for trees and so on, like tree based models. So they sort of so this I talked about this kernel shop where they sample they use linear regression to uh, like to come to this solution. But this is kernel shop. But in this paper, they also derive more kernels which are like not model agnostic. So this is actually model agnostic, this kernel shell. But as you mentioned, for like tree-based ones, they have a different kernel which is more efficient. Those sort of kernels which are targeted for each model, they have in that paper and some follow-up work, there are a couple of work. I'm not exactly sure how they perform, but uh, like I think this is widely adopted different kind of models through these efficient kernels.
And also like one more question like in this particular slide so they are using a concept and then it goes to a linear regression. So what's the labels we have to train the linear regression? So is that the
Right, right, right.
prediction or is it something?
Yeah,
Yeah,
yeah.
what's the why here? Yeah.
Yeah, to train this linear regression, this is actually the uh, yeah, this is actually the reward. I mean, the gain by adding that feature. That's the why.
Okay.
And exists that feature vector. So without doing this for all the subject, for all the uh, dashes, they want to come up with an approximate value for that. But I'm not also exactly familiar with how they compute it, unfortunately. So
Thank you.
yeah, I mostly talked about the Shapley values in this presentation, but actually, like this paper contributes much more rather than like so they sort of use this Shapley value concept as an own thing, and they unify it in a uh, theoretical manner uh, for machine learning.
Any other questions? No. right, sounds good. It's definitely an interesting approach. Okay, guys, I think like we can then wrap up for today. Who's presenting next week?
I was wondering whether like juniors have you all completed the exams, and if you all are all right with resuming, we can start from there.
We have
Before
our last one this Thursday. After that, we don't have it.
All right, then only for next week, probably we can move from the people who are here.
All right, sounds good. Okay then, guys. Okay, we can wrap it up. We'll meet again next week.
See.
See you then.
Can I submit?